Hello and welcome to a tutorial in Rocky. In this tutorial, I'm going to give my students some idea about how Rocky works. It's a discrete element method software, and students should give me a feedback about the ease of the use of Rocky before we have further decisions on the implication of Rocky in our courses. This video is sponsored by the Live Australia with the 30-day trial versions. So in the first step, I need to create a new project. And in the study, I change the name of this one will be the SAG mill. In this tutorial, I'm going to make a ball mill with some rock and steel ball and then roll it over so the steel ball will crush the rock. My customer name will be Peter To, and the description will be tutorial to give students an idea how Rocky DEM works. Alright. In the first step, we are going to set up the physics. In this, we select the contact model and select the collected information. So in the physics, I'm going to keep the default value for gravity. And in the momentum, I use a linear spring rolling limit. If I don't choose this one, my sphere going to rotate continuously at its place without any resistance. The numerical softening factor I use here will be 0.1. In the next step, I need to choose the model. I want to collect some information from my simulation. So I need to select the information I want to collect. First of all, I think I need the boundary collision statistic. I don't have any coupling with float, so therefore I uncheck the CFD. I need the intergroup and interparticle collision statistics. And I don't have any type of particle to support the intra-particle collision, so I uncheck this one. But I need information about the particle instantaneous energy, so I click on them. Now if you click on the model, you can see the four model you have selected. And you need to specify which information you want to collect. In general, you want to select all of them, but you sometimes don't need them. So for the boundary and statistics, I think I need only the intensity. For intergroup and interparticles, I think I need the energy dissipations and the power. For the particle instantaneous energies, there is no information by default. So I think this is okay for me. After the first step, we are going to import the geometry and create the motion for the mill to roll over. Now in the next step, I need to draw the geometry or input it from a 3D file. Can be drawn in ANSYS with the Space Claim or SolidWorks or Fusion 360. In here, I use the default geometry provided by the provider. So I use import geometry and I select the mill from the STL file. And I name this one as the SAG mill file. Yep, because the file has been designed in millimeter, so I have to change it into millimeter. And it was designed specifically for Rocky, so therefore I don't need to convert the Y to Z axis. I think it's okay to me. I just click on OK. Now you can see under geometry, the mill has appeared. And if you drag it over to the workspace, you can see the mill. Now we need to create some motions for the mill. So in the motion frame, you just right click at it and create motion frame. And the motion frame name should be the rotations of the mill. So mill rotation. And I will divide the motion into two parts. In the first part from 0 to 3 seconds, I'm going to accelerate the rotations, and I set the rotations acceleration to be a revolution per minute square, so should be 200 revolution per minute square. Now I add a new one and I change this one to rotation as well, and in this one I set the start time could be 3 seconds and the stop time could be infinite to the end of the simulations, and the constant angular velocity should be 10 revolution per minute. I think it's okay for me. I have to click on mu and then select the mu rotation. Now, if you see it again, you will see that the mu is rotated with the axis and then become faster and faster, and then with a constant speed. Alright, I think this is okay for me. Now, to study the deformations of the boundary, I need to assign the wire model for the mu. So, in here, I select the mu first and then go to the geometry, and in the wire model, I select the shear work proportional and I change the ratio to 510-6. In the geometry, I set the triangle size of the tessellation to be 0.5 meter. So this is a fine enough mesh for me. In the next step, we set up the materials for particles and set up the contact model. We also choose the way how we generate particles. The material for the mu is default boundary. I think I'm fine with that. But I need to create material for my particles, which is rock and steel. So in here, I right click and create new material. So this one should be my rock. And I change the density to 2800 kg per cubic meters. Now I need one more, which will be the steel. Right. And in here, I change this one to 7800 kg per cubic meters. For the Young modulus of the steel, maybe I change it to 2E11. It's a very high number. Now, after have identified them, I need to set the interaction between materials. So I click on material interactions and I select a rock to the rock. In here, I need to identify the ratio. So the statistic fraction rock to rock, I set it 0.8, 0.8, and 0.5. For rock to steel, I set this one to be 0.5. 0.5 and 0.5. For all others, like a rock to the default boundary, which is a mu, I use the default value of the simulations. I think I'm fine with that. Now just create the particle. So right click at particle and create particles. The first type of particle I need is the rock particles. And the shape must be polyhedral. In here, I need to identify the particle size distributions, the PSD. So I just add 3 lines here, for example. And I guess this one should be 0.3 for 100 passings. 0.25 for 70 and 0.2 for 20% of passing. Now material for this one, I will choose the rock particles. In the movement, I don't need to edit the rolling resistance because this one is polyhedron. If you want to see your particles, you can click on view. So here will be the rock particles. Because it's an angular particle, so it cannot rotate continuously in one place. However, it's also change the physics. So in here, I just enter the rolling resistance to be 0.35. I think this is a good number for me. Now, in the next step, I need to create a new one, which is a steel. So I create another particles and name it as steel ball. And the material will be the steel. For the size, I'm going to set it at 0.35 with 100% passing. So this will be the uniform sphere. For the movement, I'm going to set the rolling resistance will be 0.35 as I said before. I think I'm fine with this now. Now, the next step, I need to define the input where I want to inject the particles. Will it be continuously pour from the top or I generate it instantaneously from the beginning? So I click on input and right click and create a volume fill because I want to have my particles inside the drum at the beginning. So just click on volume fill and click on this. So in here, I need to specify which particle I want to input. So I set up two of them and I change the mass to be tone. For the rock, I could have 32 tones. And for the steel, I have it 10 tones. Yep. Now I need to specify the region I want to set it up. So for the region, the coordinates I want to have will be -4 by y. Yep, so you can see it's generated right here. And I try to use the mu as a reference for my generation, so it will not go over the mu. And I use the geometry to compute it. So it will be somewhere over here, generated and then drop down and then roll over. In the last step before simulations, we try to set the periodic boundary and set the simulation properties. And after that, we can start our computation. Now in the next step, we need to find the contact. So therefore, in the contact, we should collect the data. Now in the next step, I need to set the domain setting for my computation. So I set it as a Cartesian periodic domain. If the bone fall over to the other side, it could appear from this side. And I repeat it by Z because this is my X, this is my Y, and the direction into the screen will be my Z. Now in the solver, we need to collect some information about the energy spectra. So we need to specify them. So the energy spectra start at 7 seconds. And the number of particle energy spectra, I will set it at 20. And the same to the contact energy spectra at 20. So in the time, I can specify the simulation duration, the final time for simulation. So in here, I can keep it at 20. I'm fine with that. The output for simulations, I think, should be about every 0.1 second. And the where start at 7, as we specified above. Now in the general tab, I need to select the GPU or CPU. On my computer, I currently don't have any GPU, so I select CPU as my default. I have 20 processors, but this is a trial version, so therefore I can have maximum only 8 processors. And I think that is. I can start now. Now, it will take a bit time for you, so just have a rest and then I will come back in a second. Alright, So now the computation has finished and we are going to see what is the result of our simulation. So if you want to see the animation, just click on this play button. So you see that all of the particle has been generated loosely within the drum and then fall off, and then the rotation of the drum take it away and then drop down and take it up and drop down again. And you can see here the difference between the steel particles and the rock particles, but we cannot see it so clearly. So therefore, I'm going to make the coloring different. So I click on particles, and for the color, I choose a particle material. So now you can see that it has different particle material here. The steel one is red and the rock bone is yellow, and we can see it clearly now. So the rock bone falls faster because it's heavier, and also bounce less because it's much heavier than the rock. Meanwhile, the rock can be lift up very quickly and then fall and fly over because it's lighter. And this way, the bone can crush the rock during the rotation of the mill. In the next step, I would like to see the difference in the wiring model. Alright, so in here, I'm going to make a new properties. So I must click on the mill, and then in the property, I add up a new one, and it should be a radial displacement, and the output should be in meter, and I calculate it from displacement in x and y and click OK. So now you can see here I have two variables. That's the A, which is the displacement in x, and the B, which is the displacement in y. In the expression, I have it equal to the square root of A square plus B square. So this way I can have the radial displacement, and I click on OK. And now I need to color it. So therefore, I right click at the mill and then use process and make a plane. In this plane, I'm going to make this one should be the radial displacement. And I made it the position of 1. That means I cut it right at the middle of the view. And for the colorings, I'm going to use the color from the radial displacement. Alright. And the width, bandwidth, I select it to be 10, for example. Alright. Now, let's see if it can be different. So you can see at the beginning, you don't have much of the impact. So therefore, there's no displacement in radial directions. Now, after a while, you will see that it has some displacement because of the wiring model. And therefore, the color change. You can see the difference in the color over here. All right. I also can have many other options for the simulation. For example, I can have the particles by the velocity. So I just choose translation velocity, for example, like this. So at the beginning, it should be 0. Yep. And now it has some translation velocity. And the faster it is, the hotter the color is. Alright. If I'm not interested in the translation, I may be interested in the power or in the rotation velocity, power impact. Let's see if it has any difference. Yep, so that's the impact of the collisions. And now it's become more. You can see that the collisions will have different color, and therefore you can get the different colors based on the power you have for the impact. I think this is good for this tutorial. If you have any question, please feel free to let me know. Thank you for your attention. See you next time.